Fantastic. It's so wonderful to be here, to see all of you in this fantastic space. And I'm going to tell you the story of our universe. My conception of this story is that it is a detective story. So let's get started. So I'm a cosmologist. Cosmologists study the origin, the fate, and the evolution of the universe. You know, just the small stuff. Cosmology is one of the oldest branches of science, and for the very longest time, it was a very speculative subject. You can see the Flammarion woodcut behind me, a medieval person trying to pierce through the dome of heaven to see what makes the universe tick, what's behind all the lights you can see in the sky. So cosmologists today are still doing that. But cosmology is not like all the other experimental sciences. I hope you'll agree that it's a good thing that we can't make a universe in the lab. We can't make it pop into existence, poke it a little bit, change a little bit of this and that, see what happens. We can't do that. So cosmologists have to become detectives. We have to look for clues that nature itself left us and use that to piece together the story of our universe. And nature has been very kind to us. Nature has left us clues that are written and expressed in the language of mathematics, and also written in the data that we can see when we look out into the depths of space. So, one of the reasons that this is possible is a quirk of nature, which is that light has a speed limit. This is the bane of science fiction writers everywhere. Light has a speed limit. It's very fast, but it's finite. So this means that the light from even the nearest stars take years to reach us. So when we see those stars, we see them as they were in the past. And this also works when you look out into the universe. When you look out into the depths of space, we are seeing the universe as it was in the past. So looking into space is a form of time travel. So when you look out into the depths of space, eventually it starts to look very different from the modern day universe. It starts to look simpler, darker. You can roll back time in this way and see the very earliest light we can detect in the universe. We call this the cosmic microwave background. I'm going to start by rewinding all the way back to 13.8 billion years ago, when this light first came into being. So let's start our journey with the dawn's ancient light. Let's remind ourselves that we live inside a galaxy. We live inside the spiral arm of the Milky Way galaxy, and many of the maps of the universe that I'm going to show you in this microwave light are going to look like taking a whole sphere and projecting it out into a sort of ellipsoidal projection. So when you see this map, you're seeing the whole sky with our galaxy going across it, and we can observe in longer and longer wavelengths. And eventually you get to microwave wavelengths. And then you turn up the contrast by a factor of about 100,000, and you see a picture like this. So you see this red band going across this picture. That's the emission from gas in our own galaxy. So our galaxy emits in the microwave bands, so that's our own galaxy. But if you look above and below, you see these patches of blue and green. These patches indicate tiny variations in the temperature of the very early universe, and hence its density from one place to another. And this variation is very tiny. It's 1 part in 100,000. So this picture is a baby picture of the universe. This picture comes to us from a time when the universe was only about 380,000 years old. This is the earliest light we can see. And these hot and cold patches form the seeds of all of the structure that we can see in our universe today. Everything that we can see, from a galaxy to a planet to a person, came from the fact that the early universe, uneven in its density from one place to another. These tiny irregularities in the early universe grew under the action of gravity into all of the structures we see in the universe today. I'm going to lead you through the history of this ancient light and how one can learn about the universe from it. So I want to start at the very beginning with its discovery. It was discovered in 1964 by these two blokes, Arno Penzias and Robert Wilson. They were working at Bell Labs in New Jersey, and they built an instrument, a radio telescope, to look at a much more mundane thing. They wanted to study the radiation from the gas between the stars. They turned on their instrument, and immediately they were consumed by finding a hiss in their instrument that was coming from all over the sky. They got really, really obsessed about pigeon droppings. They called it a white dielectric substance, very delicately. They started scooping the stuff out. That didn't make a difference. This hiss from all over the sky remained. And eventually, I learned that there is an actual murder mystery here. Pigeons, they're home. If you take them away, they come back. So that was tried. They came back. And eventually, the pigeons were shot. Unfortunately, this hiss still remained, and these guys went down the road to Princeton University and talked to some of their colleagues who had been actively looking for this hiss, this noise in their instrument, and basically, it was the afterglow of the Big Bang. It had been predicted in the 1940s, and then it was discovered by accident in 1964. The pigeons didn't get anything, but these guys got the Nobel Prize for their trouble. I'm going to fast forward through a lot of blood, sweat, and tears to 1992. By this time, our instruments had improved enough that we could put a satellite in space and measure this radiation very accurately. This satellite was called the Cosmic Background Explorer, COBE. It made a map that looked like this and showed that this light, this very uniform light from all over the sky, was very cold. Its temperature is about 3 degrees above absolute zero. But also, it discovered something remarkable in addition. So you see, this cosmic microwave background, it has a very uniform temperature that tells you that the early universe was very homogeneous. But the universe today is extremely inhomogeneous indeed. So how did that happen? This experiment actually discovered the primordial ripples from which everything came. This is the map that they made. You can see it's very crude. The red band of the galaxy is going through the map. Above and below, you can see the primordial ripples. It's got quite low resolution, but this was the discovery image of the origin of all the structure in the universe. I want to start to show you the human face of some of these experiments as well. So Penzias and Wilson, they were just two people. They built an experiment. They made a discovery immediately upon turning it on, and they won the Nobel Prize. Nowadays, the detective work is much more subtle and challenging. So now we're starting to see teams of people, and this is a theme that I hope that you will capture as I go on with my talk, about how it takes a collaboration and the cooperation of many different people to make these discoveries. So this is part of the COBE team. I find it very enjoyable to see some of my colleagues in these weird 80s costumes. There's George Smoot. He's celebrating the Nobel Prize perhaps, but he really loves life, so maybe he's enjoying something else. And there's also John Mather here, who also got the Nobel Prize for this discovery. I also want to show and draw your attention to the machine in the background. I mean, there might be people in this room that don't recognize that this is a computer. Computers now increasingly play a fundamental role in the process of understanding the data that cosmologist detectives have to study. In 2003, a second-generation satellite launched by NASA delivered an enhanced map of the cosmic microwave background. This is the Wilkinson Microwave Anisotropy Probe. Try saying that fast several times, very, very fast. So this satellite enabled a big increase in the sensitivity and resolution from COBE. And that very crude map of the primordial ripples that COBE made came into sharp focus. With the help of this new map, we figured out the so-called standard model of cosmology. It's a model that basically describes all of the data we've collected about the universe, and I'll get to that in a little bit. But first, I want to show you part of the WMAP team as well. This is a really important picture for me personally, because I'm actually there. That was during my PhD, and you can see us looking very happy, because that day we had got our first cosmological results from looking at this map. And there's also Dave Wilkinson, who the satellite is named after, a brilliant experimentalist who sadly passed away shortly after that picture was taken. Now I want to talk a little bit about what we're seeing when we see this light. The early universe was very hot. It was so hot that electrons were separated from their nuclei. So the universe was filled with this hot soup of ionized plasma. Packets of light, photons, couldn't really get very far because they kept bouncing off all of the free electrons they were surrounded by. So the universe was actually opaque to light. Eventually, as the universe expanded, it cooled. Eventually, the temperature dropped sufficiently for neutral atoms to form, so the electrons recombined with their nuclei. Even though it was still a very high temperature, it was cold enough for the atoms to form. At that time, the universe became transparent to light. This light was then released, and since then, the light has been traveling to us through space. So why is it in the microwave? In the early universe, when it was really hot, they were not microwaves. They were very high-energy photons, gamma rays, X-rays, very, very energetic photons. But as they pass through space, they share in the expansion of the universe, so their wavelengths get stretched out by the expansion of the universe. So they got stretched out into the microwave, and that's where we detect them now. The lonely journeys of these messenger photons are extremely remarkable to contemplate. They were released 380,000 years after the Big Bang, and they've been traveling to us for over 13 billion years. During that time, before they were eaten by our detectors, they have mostly never encountered any other matter. The universe is extremely empty. So what you're seeing here is a pristine image of the conditions in the early universe. What we are seeing in the patterns imprinted in this ancient light is a cosmic tug of war. It's a battle between gravity and pressure. This sets off sound waves in the sea of electrons and photons. You can see these vibrations happening at all wavelengths, and we see these sound waves frozen in time at the time the universe became transparent. We can also hear the sound of the universe when it was very young. We can convert the data from the cosmic microwave background into sound and listen to it. So you can actually hear that this is not just one frequency, there's structure in it, right? So deciphering the meaning of that structure is what allows us to learn about the universe. So how can we use this data to learn anything about the universe? In addition to these beautiful instruments that we can build to measure the sky, we also have theories that make precise predictions for what the sky should look like. Remember, we can't do experiments about the universe, but we can calculate the predictions for what the universe would look like using different physical models, and we can compare those predictions with the data. So this map is like a fingerprint. And you can identify the culprit theory by comparing a lot of theories with the data and coming up with one that fits the fingerprint. In this process, we can also eliminate a lot of suspects from our inquiries, the theories whose predictions don't match the data. So here again, the advent of computers is very important. You need to calculate what the fingerprint looks like millions of times, and that usually requires a huge amount of supercomputer time to analyze all of that data. And when we do that, what we find is something rather surprising. The map that WMAP made is about 3 megapixels in terms of its image. All of the information in that image is well described by only 6 numbers. These 6 numbers tell us the shape, the age, and the clumpiness of the universe, and its constituent components, atoms, dark matter, and dark energy, and also when the first stars formed. So the model of the universe that describes this data seems surprisingly simple. However, the simple model still contains 3 ingredients which are not in our standard model of particle physics. This dark matter and this dark energy, and the early universe was clumpy. So what made all of the structure in the early universe? These 3 ingredients are not in our standard models of physics. So the universe is simple, and yet it's bizarre and strange. So it's time to take stock. I'm going to show you now what we have learned so far about the universe and show you the history as we understand it now, following WMAP. We're going to zoom into a cold spot in the primordial soup. This is a place where there's more mass than average. So matter is attracted to matter by gravity. And as chunks of matter start coming together, recognizable structures start to form. The universe is dark till the first stars turn on. Matter evolves into filamentary structures traced by galaxies. And we are looking through all of this turbulent history at the earliest pristine light. Now we come to Planck. This is a European Space Agency satellite that was launched in 2009. Planck, being the 3rd generation CMB satellite, is on a different scale of complexity and ambition from previous CMB experiments, both in the technology that was used and the number of people involved. So you can see this is part of the Planck team. The size of the team has grown even more. The success of this mission is a testament to European cooperation and the collaboration of scientists from all over the world. Planck operated way out beyond the orbit of the moon, just like WMAP, and its detectors could measure the temperature differences of 1/1,000,000th of a degree, which is like measuring from the Earth the heat produced by a rabbit sitting on the moon. To achieve this, some of Planck's detectors were cooled to about 1/10 of a degree above absolute zero. So when these detectors were operating, they were the coldest place in the universe. This was done so that their own heat doesn't swamp the signal from the sky. As a result of Planck's 50 megapixel map, the baby picture of the universe sharpened yet again, and we measured the parameters of our cosmological model to percent precision. Here's an example, Planck's measurement of the age of the universe, 13.82 plus or minus 0.05 billion years. This is answering a question that humanity has asked since the dawn of history with 0.5% accuracy. Now I want to rewind time even closer to the beginning. With data of this quality, we set out to answer one of the more audacious questions that I asked at the beginning of the talk. The precision of the Planck data allows us to rewind time back to an instant. This is a decimal point followed by 32 zeros and a 1, a tiny fraction of a second after the beginning. This takes us tantalizingly close to whodunit. Where did all of the stuff in the universe come from? At this very early time, we think that quantum ripples in a so-called scalar field, we call it the inflaton field, seeded all of the structure that we see in the universe. During the same infinitesimal instant, the inflaton is thought to have caused the universe to blow up by a factor of at least 10 to the power 26 larger, in a process we call inflation. The universe grew so fast that not even light could keep up. and space became flat and smooth throughout our observable patch. At the same time, the tiny quantum ripples in this field got stretched out by the expansion of the universe to become the seeds of all of the structure we see in the universe today. So then, 380,000 years later, you see the imprint of these primordial ripples in the cosmic microwave background, starting off the story of the universe I presented to you earlier. This idea that everything in the universe arose in tiny little quantum fluctuations can sound like science fiction. Till the discovery of the Higgs boson, even the concept of a scalar field was completely hypothetical. But now we know that nature contains at least one scalar field. However, inflation is still a big extrapolation of physics. This is a sort of here be dragons point in the history of the universe. So, how do we test this idea? This theory is a big extrapolation of physics, but it has the virtue of making precise predictions. For example, it says that the power in the CMB fluctuations should be distributed as a function of wavelength in a certain way. Let's get some intuition about this using an analogy with sound. So you can think about the information in these maps in analogy with listening to a piece of music, and try to figure out whether the universe has more power in the bass or in the treble. So the very largest length scale in the universe are the longest wavelengths, so they are the bass, and the short length scales are the treble. Using the map, we can measure whether there's more power in the bass or the treble. The theory of inflation makes a detailed prediction for what you should see. So imagine that there was more power in the treble compared to the bass. So a treble-heavy universe. That would sound like this. If the universe had more power on large scales rather than small scales, it would sound like a bass-heavy piece of music, like this. If the universe had roughly equal power on large and small scales, it would sound like a balanced piece of music, like this. Thank you, Mr. Bach. So Planck has measured very precisely that the universe sounds roughly balanced, a little bit bass-heavy. That's exactly what inflation predicts. So the inflation theory was not the only suspect in town for what was the cause of all of the structure in the universe to be originated. There were other theories, such as cosmic strings. These are one-dimensional defects in space, or textures, which are like swirls in space. These theories also made very precise predictions for what you should see in the cosmic microwave background, and the data didn't turn out to look like those predictions. So these suspects were eliminated from the inquiries of the cosmological detectives. Many people worked on different kinds of theory for many years. Sometimes entire careers were spent on working on theories. When the data came in, those theories were wrong. Here I want to make a really important point, which is that looking and not finding is not the same as not looking. You have to test theoretical predictions with data. And if the theory that you worked on disagrees with the data, your time has not been wasted because you've still learned something. You've learned that the universe works a certain kind of way and not another kind of way. This is extremely valuable information to the cosmological detectives who are trying to extrapolate way beyond laboratory-tested physics. Now I want to talk about the dark side of the universe. Let's turn to the very bizarre fact that the universe is mostly consists of stuff that we cannot see. Most matter made of stuff like us, the matter described by the standard model of particle physics that we have tested at CERN, that's only 5% of the universe. 80% of the matter in the universe is dark matter. But matter is not even the main constituent of the universe at all. Nearly 70% of the universe is made up of dark energy. So it might sound like we don't know what you're talking about when you're calling things dark. If you say that, you might actually mostly be correct. We are talking about ingredients whose effect that we can very clearly measure, but which do not fit into the standard model of particle physics. We actually have more idea about what dark matter could be than what dark energy could be. For dark matter, there are many extensions to the standard model of particle physics that might give us candidate particles that interact very weakly with ordinary matter. And therefore, they would be very hard to detect and would be invisible. That can also cause them to dominate the matter content of the universe. Dark energy is a different kind of beast. It's making the expansion of the universe accelerate. It's been doing that for 1 billion years, and it's not going to stop. This is expected to lead to a very cold, sad end to the universe, many billions of years from now. But we don't know what it is. We can only measure its effect on the universe. Dark energy is here be dragons territory, and we will characterize its impact on the universe better and better in the coming years. But understanding it would require a breakthrough in theoretical physics. However, we can learn a lot about dark matter in the coming years, so I'm going to talk about that now. An obvious way to view the universe is invisible light. There's a reason our eyes have evolved to see the world at optical wavelengths, because the sun has significant radiation output at those wavelengths. So starting in the 1990s, we have been viewing the universe in starlight, mapping it in very deep and large-scale galaxy surveys. This is part of the Sloan Digital Sky Survey. This is not a simulation. Each one of these galaxies is a real object. There are about 400,000 galaxies in this animation. I could stare at this for hours. It's like a swarm of fireflies flying through the night. And they congregate, they cluster, they don't scatter randomly in space. Well, why do they congregate? It's because they're tracing huge filaments of dark matter that you can't actually see. You can't see 80% of the matter in this image. This is a slice through a simulation of how galaxies trace dark matter. When you look at this image, it may perhaps remind you of seeing the Earth from space at night. So before the invention of electricity, you couldn't really make out when you looked at the Earth from space at night where the continents were, where the oceans were, and so on. But now that we have electricity and we have cities, you can look at the Earth from space at night and you can see the outline of the continents. You can see that there are land masses. This is, of course, a biased measure of where the land is because it traces where people live. You're not going to make out Antarctica, for example. Similarly, galaxies trace the dark matter in a biased way. You can simulate how they populate the underlying dark structures. So here is such a simulation. Again, you can see the utility of supercomputing power in cosmology. This is a simulation of a formation of what's called a cluster of galaxies. Galaxy clusters are the largest structures that are in the universe. They're massive multiplexes of galaxies. They blow out huge plumes of gas as they form, and eventually these assemblages start to look like the clusters that we see in the real universe. So how can we use this to figure out what the dark matter is? It's a little bit like how we figured out the standard model of cosmology. Using computer simulations, we can make detailed predictions for the fingerprints of different types of dark matter, which will alter how galaxies are scattered in the scaffolding of dark matter. By extracting how such structures should look at different wavelengths, we can compare those predictions to the data and figure out which one of these theories match the data and which don't. This research is currently underway. This research requires a lot of supercomputing power. You might remember when I showed you the picture of the Kobe detectives, there was a little desktop computer lurking in the background. Nowadays, we use machines like this. It's a big supercomputer that runs big computer codes and makes precise simulations of what the universe should look like. But on top of that, our data sets are growing. They're getting so big that we need completely novel ways to analyze it. A human being could sit there and spend their entire lifetime going through that data and not be able to look at even a tiny fraction of it. It's big data, and it needs big algorithms. I'm currently working very hard on preparing for the ultimate big data project. This is the Vera C. Rubin Observatory, which is going to start operations in a couple of years. Rubin will carry out a 10-year survey of the whole sky. The pictures of the universe I've shown you so far are static. They're frozen in time. Rubin will return to every patch in the sky every 3 days or so for 10 years. And by stitching together those images, we can make a movie of the dynamic universe. This will enable us to study space and time in a way that has never been done before and enable diverse science missions at the same time. Rubin will create a data deluge, and people from different communities have come together to make sense of it. These include not just cosmologist detectives, computer scientists, data scientists, and statisticians are joining us. In the last part of my talk, I want to return to the origin of structure and how it relates to black holes. Everybody loves black holes, so do I. So remember, the theory called inflation, where the universe created all of the structure in it from quantum fluctuations. So this theory makes an extra prediction. If inflation happened, it should have set the whole universe ringing like a bell. The resulting ripples in the fabric of space are called gravitational waves. There are many different types of evidence that we can seek as cosmologist detectives. There's the absence of evidence, which rules out theories. There's circumstantial evidence. For instance, the type of evidence we've accumulated so far, which makes us think that even though inflation is a strange, exotic idea, it may capture something about the real universe. And then there is the smoking gun evidence that would demonstrate beyond reasonable doubt that we are on the right path. Gravitational waves from the primordial universe would present such smoking gun evidence in favor of inflation. This is very exciting because there is an avenue to find this smoking gun. That's because the cosmic microwave background is polarized. That means that the light makes up the cosmic microwave background, it vibrates preferentially in a certain direction. So it has a handedness. The texture on these maps indicates that preferential direction in a certain visual way. I really love this visualization. It's like a Van Gogh painting. It gives an impression of the polarization pattern on the sky. If there were gravitational waves in the primordial universe, that would imprint a faint signature onto this polarization pattern. It's a very small signal, and it's extremely difficult to observe. You have to do it from very cold, high, dry places on the planet, like Antarctica. I have friends who winter over at the South Pole, working on telescopes in the dark, many months on the end, because they want to be the first to detect this gravitational wave signature. Until 2015, we didn't know whether the universe could make gravitational waves, and that's where black holes come in. So what you're seeing here is a simulation of two black holes spiraling in together, and eventually they will merge. The arrows are the swirls of space near the deep gravitational wells of these black holes. It's going to slow down in a little bit, to show you the final merger of the event horizons of these black holes into one. This merger event creates a burst of gravitational waves, and these gravitational waves then spiral out into the universe, and a very lucky human being might have a chance to detect them. It's going to go off in a minute. Boom, there it goes. So we've seen the universe, we've heard the universe, but we can also feel the universe by measuring these waves. So 1.3 billion years ago, gravitational waves were created in the violent merger of two black holes in the distant universe. 3 times the mass of the sun got turned into energy in a fraction of a second. The burst of gravitational waves arrived on Earth on the 14th of September 2015. And it made a minute change, a tiny fraction in the diameter of a proton change in a mirror in an observatory called LIGO, which is one of the most amazing things that human beings have built. LIGO is now a gravitational wave observatory. It routinely detects merging black holes out there in the distant universe. But for the first 25 years of its existence, it was just an instrument for measuring noise. Can you imagine spending 25 years of your life measuring noise better and better so that you can detect waves crashing on the rocky beach, so that you can detect the jet engines of aircraft flying overhead? That's what they did, minimizing that noise and understanding that noisy background so well that you can detect a signal that moves your mirror by the fraction of a diameter of a proton. That's like measuring the distance between the Earth and the nearest star with the precision of the width of a human hair. It's an incredible technical achievement. They also have 2 different instruments, so widely separated that they can be sure that the signal is coming from out there in space and not from the local environment. This persistence and patience paid off with a groundbreaking discovery that has opened a completely new window onto the universe. So just like electromagnetic waves, gravitational waves can have different wavelengths or period. And by changing the size of your instrument, your detector, you can detect different types of sources. So LIGO detects sources like black hole mergers that produce waves with periods of the order of milliseconds. In the coming decades, a space-based laser interferometer called LISA will let us detect waves from much more massive black holes with millions of the mass of the sun that lurk in the hearts of galaxies. You can also use pulsars, which are spinning neutron stars. These are dense spheres of exotic nuclear matter. They're roughly the size of Copenhagen. You can use these as a natural network to try to detect passing gravitational waves, sort of like a natural laboratory. To tie it back to the origin story of the universe, the gravitational waves produced by inflation would have periods of billions of years. And to detect them, you have to use another natural laboratory, the cosmic microwave background. In the last couple of minutes, I want to show you a mind-blowing implication of inflation. If it's a correct description of nature, inflation doesn't just make the observable universe. It makes a big universe, much, much bigger than the observable universe. Even more bizarrely, that's not the end of it either. It will create structure on huge scales beyond the observable universe. It will create other universes, bubble universes, with our universe just being one among innumerable others. That's the implication of this theory. It sounds like science fiction. But this implication is something we have to grapple with and work out a way to test if the clues continue to fall into place and point the finger at this theory. So by definition, it's not going to be possible to test predictions for what happens well outside our own universe by looking at cosmological data within our own universe. We can't make universes in the lab either. That's probably a good thing. One way we have been exploring to test this implication of the theory is to try to emulate the same physical equations, but translated within an analog condensed matter experiment in the laboratory. This involves ultra-cold atom systems called Bose-Einstein condensates, where phase transitions in the laboratory experiment can be measured and compared with the predictions of the cosmological analog theory. This means that we can at least be confident that the extrapolation of theoretical physics that is leading to this startling implication of a multiverse is actually accurate. A prototype experiment is now being built, so watch this space. So this is a modern version of the Flammarion woodcut that I began the journey with. We have learned a lot. We have been able to answer some of the questions that people have been wondering about since the beginning of history. We have found that the universe is both simpler and stranger than we ever imagined. We have found our origins deeply tied into the quantum world. We've looked at, listened to, and felt the universe, giving us clues to figure out our origins and our fate. So often, when one learns about scientific breakthroughs, somebody's getting a Nobel Prize, everything's settled, everything is so certain by the time that happens. I hope that hearing about the process of these discoveries actually tells a better story of what doing science is like. There is a lot of lead time into making those experiments work. Whole careers can be spent working on theories which turn out not to be correct. There's audacity in that. There's courage in that. People can be wrong. There can be many blind alleys, but the scientific process is self-correcting. There's a lot we don't know, and there are very simple questions that a child can ask about what I've talked about today, where I'd have to say that the answer is nobody knows. So rather than being a collection of facts, this is a process of exploring into the unknown. By using the methods of detectives, we will hopefully continue to work out the story of our universe in more extreme regimes, further back in time, and into the distant future. Thank you.